everybody. So today I'm recording the video for 7.2 trigonometric integrals. I've decided to record and just speak about my filled in notes just for the sake of time. This one was lengthy. There's a lot of examples and I can't really leave any of them out because they're all distinct in their own way. All right, so with trig integrals, we're going to be using a combination of, first of all, trigonometric identities, substitution, and integration by parts. Okay, it'll be important to recognize what do we have and what could we possibly work with. And there's going to be plenty of times in these types of problems where we try and then try again because something just doesn't work out for us. Okay, so I'm going through a variety of examples to hopefully give you a taste of what each one might lend itself to. So the first one is an odd power of sine x. We can recognize that we can pull out a sine x and that would leave us with a sine squared x, and then we can use our identity that sine squared x equals 1 minus cosine squared x. That will be a common identity used throughout this section. By allowing us to do that, we can name our u cosine x. Du then becomes negative sine x dx. So this became a simple substitution integral once we have rewritten in the beginning work. Okay. So my rewritten integral is negative integral of 1 minus u squared du, which integrates to u cubed over u minus u plus c. Resubstitute for u, 1/3 cosine cubed x minus cosine x plus c. So that works for odd powers of sine as well as odd powers of cosine. Here's a combination where we do have a product of sine and cosine together. Similarly though, we're going to identify where that odd power is. So in this case it was with the cos. So I take one of the coses out and I'm going to rewrite cosine to the fourth as 1 minus sine squared x quantity squared. Right. In doing that, I name my u sine x. My du becomes cosine x. So when I substitute back in, even though it's a little more complicated than in example 1, I still can rewrite everything with respect to u. U to the fourth times quantity 1 minus u squared squared du. You have to expand this right to standard form so that we have individual power terms. U to the fourth minus 2u to the sixth plus u to the eighth du. And then I can antiderive each individual term, bringing me back to u to the fifth over 5 minus 2u to the seventh over 7 plus u to the ninth over 9 plus c. And final answer is 1/5 sine to the fifth x minus 2/7 sine to the 7x plus 1/9 sine to the 9th x plus c. Okay, so recognizing where that odd power was, factoring one of them out, and then substituting the Pythagorean identity of cosine squared x equaling 1 minus sine squared x here was the key. Okay. The next couple of examples are going to be using this reduction formula for sine and or cosine. Okay. So here I don't have that odd power, so I can't rewrite this, and if I chose to and I tried to use the u, then I wouldn't have any replacement for my du. It just wouldn't work out, right? I don't have all of the pieces that I would need. So the reduction formulas up top here allow us to replace sine to any power of x with the equivalent. So I followed along, and the first line of work shows that it becomes negative 1/4 sine cubed x cosine x plus 3/4 integral sine squared x dx. So I still have another reduction formula that I have to apply again because sine squared x as is, I cannot integrate it. So I'll keep going, negative 1/4 sine cubed x cosine x plus 3/4 quantity, and this one reduces to negative 1/2 sine x cosine x plus 1/2 integral of dx. And if I reduce that exponent by 2 here, the sign is gone. So final answer, negative 1/4 sine cubed x cosine x minus 3/8 sine x cosine x plus 3/8 x plus c. Of course, pause this video as much as you need to, slow me down. But again, I think for the sake of time, otherwise this video might be 45 minutes plus in length if I didn't talk over my writing. Okay. So a few more identities that may or may not get applied, but kind of keep them in your back pocket. they're verified with different trig identities shown on the right, but the integral of sine squared is equivalent to what we just saw, and cosine squared is there as well. So it's kind of a little bit more background information on where did those previous reduction formulas come from, and sometimes just going directly to this can be helpful. All right, example 4 shows us where we have even powers of sine and cosine together. And how do we choose which replacement to use? All right, depending on which exponent is larger, that's what we go with. So in this case, m is less than n, so the sine exponent is less than the cosine exponent. So we are going to replace sine squared with 1 minus cosine squared x. This turns everything into a cosine. Right, we can expand it, and we have now two integrals of cosine to the 4th x minus cosine to the 6th x. If I had gone the other way, then I would have had to, FOIL something out. It would have been a little bit more complicated. So this is just the direction that I want to go in. It also will help in the long run when I'm doing the reduction formulas. Okay. So the suggestion is to reduce the larger exponent first. That way, you might have, it's not always going to happen, but you can have a time where you can combine like terms. So if I use the reduction formula from the previous page, I have the integral of cosine to the 4th out in front minus quantity, 1/6 cosine to the 5th x sine x plus 5/6 integral cosine of the 4th power x dx. So now I do have those like terms, right? I have the integral of cosine to the 4th x dx minus 5/6 integral cosine to the 4th x dx. So I can combine those two through subtraction. And now I'm left with negative 1/6 cosine to the 5th x sine x plus 1/6 times the integral of cosine to the 4th x dx. So I'm going to have to still reduce again, but at least I'm down to just two terms. I continue my work on the next page. So that reduction for the cosine to the 4th is 1/4 cosine cubed x sine x plus 3/4 integral cosine squared x dx. As I go down each line of work, I continue to bring everything with me. The textbook doesn't. I would always just fear that I forget a term, so I copy everything down each line of work. So I'm simplifying, I'm distributing along the way, I'm careful of my positives and my negatives, and then I still had to do the reduction formula one more time with the cosine squared. So the reduction formula with just the cosine squared is the 1/2 cosine x sine x plus 1/2 x, and I have a plus c at the end. So my final answer with all of my fractions, negative 1/6 cosine to the 5th power x times sine x plus 1/24 cosine cubed x times sine x plus 1/16 cosine x times sine x plus 1/16 x plus c. Okay, so example 5 now brings us to kind of proving tangent and secant, right? The tangent integral we did back in substitution, so that proof is nothing new to us. It does get rewritten as ln absolute value secant x plus c at the end, and there's just a little subtle trick there, which we may or may not have covered in chapter 5 when we first took a look at this. But anyways, replace tangent x with sine x over cosine x, name cosine x your u, and derive it. So du is then negative sine x dx. So you're integrating negative du over u, which becomes negative ln absolute value cosine x plus c. So that's really a property of ln's where that negative 1 could bump up as an exponent. So instead of having the negative out in front, I really have cosine x to the negative 1st power, or 1 over cos x, or secant x. So that's where that one comes from. The other one takes a little bit of trickery, right? So we're specifically picking u equals secant x plus tan x simply because it works out in the end. So this was proven, obviously, long time ago. It was not an easy problem to prove, and this is what was used in order to prove it. So we're allowing secant x plus tan x to equal our u. So my side work over there in red. Therefore, my du is then secant x tan x plus secant squared x dx. I can factor a secant x out, leaving me with tan x plus secant x dx. That tan x plus secant x factor is my u. So then I have secant x u dx, and all of this still equals du. So I can divide by u so that I'm separating, right? So now my left says du over u equals secant x dx, which is exactly what my original integral starts with. So now I can truly do substitution, and I have the integral of du over u, which integrates to ln absolute value of u plus c, and I can put that secant x plus tan x back in at the end. So we kind of started with something a little bit unsure of it, right? And then we worked through a lot to finally get the substitution that we needed, which is not the common direction that we go with for substitution. Usually substitution is the clear cut. I see it in the integral, I'm replacing it with this. So this was just a proof. It's not something that you'll have to continue to do. But now you could use this if it came up. Okay, so using a table of integrals. So at the end of this section is a very long 25 integrals, I believe, is in there. And many of these next examples relate to some problem in that table. Okay. So the integral of tan to the m power of x dx is equal to tan of m minus 1 of x divided by m minus 1 minus the integral of tan to the m minus 2 power of x dx. So using that, we can evaluate the integral from 0 to pi over 4 of tan cubed x dx. So I apply that reduction formula, and I immediately get tan squared x over 2. I have to evaluate that from 0 to pi over 4 minus the integral of tan x dx. Because I've just proven tan x dx integrates to ln absolute value of secant x, I can then directly use that in my work here. So on the left now I have tan squared of pi over 4 over 2 minus tan squared of 0 over 2, quantity, minus ln absolute value secant x from 0 to pi over 4. So I just go through and I evaluate. I have 1/2 minus 0 minus quantity ln, what turns out to be ln of root 2. Distributing my minus sign, I get a plus ln of 1, which is 0. So final answer of 1/2 minus ln root 2. Okay, here's another one where I'm using specifically number 20 from the reduction table. I am evaluating tan squared x, the integral of tan squared x times secant cubed x dx. And I'm also using the fact that tan squared x equals secant squared x minus 1. Okay. So similar to that example with the sine and the cosine, I'm replacing the lower exponent with a trig identity. So now I can rewrite this integral as just secants to some powers, and I can use that reduction formula. So I have two integrals now, secant to the 5th power and secant to the 3rd power, and I'm reducing the higher exponent 1 first. So secant to the 5th power reduces to tan x secant cubed x over 4 plus 3/4 integral secant cubed x dx minus the original integral secant cubed x dx. Combine like terms and do the reduction formula for the secant cubed x, carrying everything along with it, right? So I have tan x secant cubed x over 4 minus 1/4 times the quantity, tan x secant x over 2, plus 1/2 integral secant x dx. So I've gotten to a place where I don't have to use reduction formulas anymore. I know the integral of secant x, so I get to my final line, my final answer. Tan x secant cubed x over 4 minus tan x secant x over 8 minus 1/8 ln absolute value secant x plus tan x plus c. Okay, one more example in this section. And now we have a sine of mx times cosine of nx. And this one uses reduction formula number 24. And we're integrating specifically from 0 to pi sine 4x cosine 3x dx for this example. So I've written reduction formula number 24, and I begin immediately using the reduction formula. So it says that based on m being the coefficient inside of the sine and n being the coefficient inside of the cosine, I have negative cosine of 4 minus 1x over 2 times 4 minus, I'm sorry, let me back up. I should have said negative cosine of 4 minus 3, which is 1x, over 2 times 4 minus 3, so I just have a 2, minus cosine of 4 plus 3x, so 7x, divided by 2 times 4 plus 3, or 17, all from 0 to pi. So evaluating with my limits of integration, f of b minus f of a, I would end up with a negative cosine pi over 2 minus a cosine 7 pi over 14 quantity minus quantity negative cosine 0 over 2 minus cosine 0 over 14. So from here I get 1/2 plus 1/14 minus quantity negative 1/2 minus 1/14. Nothing cancels. Opposite signs flip. We add them all together and you get 8/7. Okay, so that is the end of this section. I recognize that this style of video might be a little bit different than the ones in the past. Hopefully you're able to slow it down, pause it. If you have specific questions, obviously we'll go over them in class, but I didn't want to post a 45-minute video of me writing out all of these little details. So hopefully this was enough for you to follow along, understand where I was pulling the reduction formulas from, and how I was arriving at the final answers.